Hello everyone, this is Hongjae Hwang from KAIST. I'm pleased to present our work on JUSTGen effective test generation for unspecified JNI behaviors on JVMs. This is a joint work with my colleagues Sungho Lee, Chi-Yoon Kim, and my advisor Seokyoung Yoo. Before going into detail, let me briefly introduce you to JNI. JNI stands for Java Native Interface, and it provides a way for Java applications to interoperate with native code written in C and C++. Using JNI, Java application can call functions in native code, and similarly, native code can call functions or accesses classes and fields in Java applications. JNI is very useful in developing efficient Java programs by moving performance-critical logics into native code. Moreover, JNI allowing Java application to reuse standard library implemented in C and C++. So JNI indeed gives some benefits to Java developers. And most of the popular JVMs support JNI operations by complying JNI specification provided by Oracle. Even though JNI gives some benefit to developers, it is not easy to develop correct JNI program because of interoperations of two different programming languages. Moreover, there are no good tools for debugging and validating JNI programs, so it is difficult for developers to debug when there are hidden bugs in JNI programs. Because there is no good debug tools for JNI program, it would be great if JVM validate invalid usage of JNI functions automatically in runtime. So in order to understand whether JVM properly validate the invalid usage of JNI functions, we developed a framework called JUSTGen. The input for JUSTGen is a JNI specification expressed in our domain-specific language. JUSTGen first automatically converts input data to bit vector expression where SMT server can understand. Then JUSTGen finds unspecified cases by utilizing SMT server. Our tool found 34,990 unspecified cases. JUSTGen then creates test program triggering the behaviors of identified cases automatically. By running the test program, we evaluate the JVMs. In this research, we evaluate 5 different mainstream JVMs, including Hotspot from Oracle and OpenJNI from IBM. The unspecified cases are 1 cases of invalid usage of JNI functions, which we believe that JVM should validate. I will give an examples of unspecified cases in next slide. And please refer to our paper for more information on our tools and methodologies. So let me give an examples of unspecified cases in JNI specification. This screenshot shows the JNI specification explaining throw new JNI functions. It says that the second argument of throw new function should be a subclass of java.lang.throwable class, and the value must not be null. However, it does not explicitly explain the JVM behavior when non-throwable object is passed to the second argument of throw new JNI functions. We call such cases as an unspecified case. During this research, we encountered that JVMs do not validate almost all of the unspecified cases that we have found, which seems very bad. We have communicated with JVM vendor for these issues, and they said that they intentionally not validate them due to the performance issue. Moreover, they pointed out that JNI specification also says that it is the developer's responsibility not to misuse JNI functions. So this is the reason why JVM does very little error checking in JNI interoperations. The part of the JNI specification that the JVM vendor pointed out was captured in this slide. JNI specification indeed delegate their responsibility to developers, not to JVM vendors. But we also found Xcheck JNI option in JVM. This is a debug option. When this option is on, JVM do additional validation on the argument passed to JNI functions. And our communication with JVM vendor revealed that they want to validate as many error cases as possible when this option is on. So in this work, we evaluated Xcheck JNI capabilities in 5 different mainstream JVMs using unspecified cases. By running our 34,990 test cases, we found a lot of abnormal behaviors from JVM due to the lack of validations. Even debug option is turned on. We summarized the result into 4 different categories: misbehave, Sackford, exception, and validation. The misbehave category represents that test cases terminate normally without any warnings or error. Since behaviors of unspecified cases are not defined in the JNI specification, each JVM may produce different execution results. Seg4 represents that the test case calls segmentation fault and crashes the JVM. The exception represents the JVM throws exception while executing the test case. And the final validation category represents that JVM properly validates the test cases and terminate with an error or warning message. For misbehave category, we found 12 abnormal behavior from JVMs. Among them, I will explain one finding due to the time limitations. Please see our paper for other findings as well. So our first finding in misbehave category is error handling issues. This is the case where JVM returns incorrect return values. The upper side of the slide shows the test case in source code level, and the bottom side represents corresponding JNI specification. The register native functions is a JNI function which registers the native function received as a third argument, and the first argument represents the number of native functions to be registered. As stated in the JNI specification, the fourth argument must be number greater than 0. Our tool found that passing negative number as the fourth argument is an unspecified case, and by running test case triggering such unspecified case, we found that all of the 5 JVM could not validate the negative value even debug option is on, and the test case is executed normally without any errors or warning message. And if you look at the specification below, the return value for this function, 0 means success and negative number means failures. Fortunately, in the case of OpenJNI, it returns -1 as the return values, but other JVM returned 0, which indicates the function is executed successfully. In this case, if the developer handles the exception case by return value, the program may not operate normally. We also studied in which case triggers the segmentation fault. There are a total of 4 cases. Missing type check is where the usage of incorrect type of values or objects. For example, from reflected method expect to receive java.lang.reflect the method or constructor type of object as a second argument. Our tool found that passing throwable type of object as a second argument of from reflect method is an unspecified case, and it triggers segmentation fault on all 5 JVMs. We also found that segmentation fault occurs because of missing null check and liveness checks and releasable check. The missing liveness check is the case where deleted reference objects or values are used in JNI programs, and the missing releasable check is the case of releasing on objects that cannot be released. We did not further explore the cases where JVMs throw exception because we think that is the correct behaviors from JVMs. Instead, we further studied validation category. Here we compare the debug capability between different JVMs. As we can see from the table, OpenJNI validates most unspecified cases compared to other JVMs. Moreover, we also found that Zulu and Creto JVM validate exactly same number and type of unspecified cases, which indicates that they have same debug capabilities. Hotspot and GraalVM also have very similar debug capability to Zulu and Creto. Only OpenJNI has a significantly different debug capability. But there were no perfect one. As you can see from the table on the lower left, there are cases where Hotspot validates but OpenJNI does not. And the table on the lower right shows the unspecified cases where all 5 JVM could not validate. So when validating JNI program, it is recommended to utilize debug capabilities from multiple JVMs that will cover more misuse cases of JNI functions. We reported 792 cases and 563 cases are currently fixed by OpenJNI. The OpenJNI community was very active and they released patches very quickly. We are expecting other JVM vendor also releases patches in the near future. Thanks for listening my talks, and I'm more than happy to take questions.
Hello everyone, welcome to this new section of the conference. The first paper of this session, JUSTGen, effective text generation for unspecified gene behaviors on JVMs. The author is Yungai Wang, and he's here to answer any questions. I'm Ignacio Panac, and I'm going to be the chair of all these sessions. So please use the chat to ask any question to the author. So my first question is how do you measure test effectiveness in your work?
Okay, so basically we manually measure our test effectiveness. As shown in the paper, our tool found 34,900 unspecified cases in JNI specifications, and since there are many unspecified cases, it was impractical to investigate them all. So instead, we choose one unspecified cases for each parameters of JNI functions, and we actually manually execute the test cases and see how it goes, whether JVM works properly or whether there where there are some issues in JVMs. So we manually measure our test effectiveness.
And in what sense this measure is objective? I mean, does it depend on any experimenter, or you follow some kind of protocols to ensure that the metric is the same independently of the experimenter?
We just experimentally run the 5 different JVMs by running the selective unspecified cases, the test programs, and we compare the behaviors of these 5 different JVMs to check whether it's working normally or not. So basically, we perform the differential testing to see the correct behaviors of JVMs.
Okay. My next question is about another possibility to apply your approach. It's more focused on graphical user interfaces. In what sense this approach could be applied also to graphical user interfaces? Because there are many times where testing is focused on functionality and we forgot evaluating graphical user interfaces, while these kind of interfaces are very important for end users. So in what sense this approach could be applied for evaluating or testing graphical user interfaces?
Currently, our tool does not support GUI because the main purpose of our tool was to validate the JVM implementations about the JNI support. So our tools are currently running on as a command line by running a JNI program, triggering the behaviors of unspecified cases. But the maybe as a future work, we could support GUI. So for this work, we targeted 5 mainstream JVMs, including Hotspots and Oracles and IBM's OpenJNI, but we did not work on the Android because to test Android, we need to run the emulator, like we need some GUI. So maybe as a future work and by adding a GUI, we can evaluate the Android by approaching the same methodologies explained in this paper.
Okay, thank you. And my last question is just about future work. I guess this is a first step or a middle step in your research. What are next steps you are thinking to conduct in next month?
Okay. So in this work, we show that JVM do not validate misuse of JNI functions. So even debug option is on the JVM do not validate thousands of unspecified cases, and because of that, some bad things are happening here. So as a future work, and this is currently ongoing our work, we are developing automated framework for validating misuse of JNI functions. And to make this as a practical, we are developing it as a way that it is independent to the JVMs. So that is one of our future work. And the another future work we can think of is that, as I mentioned, that we excluded Android in these works. So we may apply the same methodologies in Android and verify Android's JVM as well.
Okay, thank you very much. So if there are no questions from other attendees, I think we can close here the question and answer sessions. So receive a virtual clap from all the attendees. And if any attendee has any comment or question, you can meet the author in the discussion room. Okay. So see you in the next paper.
Okay. Thank you.
Bye bye, Jai.
Bye.
Good work.
Thank you.